Okay, so earlier we talked about how you can take in propositional logic TFL, that system we were doing before first order logic. If you started with sentence letters, these are these capital letters that represent an idea in first order in propositional logic. And then you create sentences by combining those letters with ands and ors and implies, if and only if, and negations. And we kind of built up all the formulas of TFL from those sentence letters and the connectives. So we have a similar kind of definition of sentences in first order logic. Um, so here's a reminder and a recap of all the stuff we have. So in first order logic, we have predicates, and those are things like is a dog, okay? Things that'll have usually have a variable in them, and we use names in those names and variables in those places where there's a missing item. We have names, which uses the letters A through R, lowercase, and allows subscripts on them. We have variables, which uses S through Z, lowercase, and then we also allow numerical subscripts on them. We have connectives, and these are the connectives that we've used the whole semester: negation, conjunction, disjunction, implication, and biconditional. We have the brackets to make things clear, and we have these quantifiers that we covered last week. So all of this together is going to be the system of first order logic. We will write proofs in this system eventually, but for now we have to talk about what is a sentence in this language. So just like before, there's this notion of an expression, and that is just writing any list of symbols down. It's nonsense. For example, if you were talking about English or something, that is an expression. It's a meaningless string of symbols, okay? And that's all they're saying here. We needed some term for that, okay? Because some expressions are formulas and sentences, and others are not, okay? So, a term is what we use to talk about both names and variables at the same time, okay? Because a name is usually referring to a specific name, like Tom is a name, whereas X is a variable and it could take many values. Usually variables are occurring within an expression with a quantifier, and names are either something you do in advance, or we'll see later things that are going to arise out of removing a quantifier from a statement, like in a proof. So a term just is the word for names and variables. Okay. So they start the exact same way we did with propositional logic. So atomic formulas, they say any sentence letter is an atomic formula. I think they mean any term is an atomic formula. That's a typo, because sentence letter was the word we had earlier when we were doing propositional logic. It is not the word we have in this thing. So if we have an n-place predicate, that means you have n places that you can put in a name, and then these are terms, then this thing's an atomic formula. So what this is saying is, if we take a predicate that is one of these things, and then we fill in all the gaps that are appearing there, then that's also considered an atomic formula. We treat equality special. Okay, the last video I made was about equality, and that is just the statement that two terms are equal is a formula, and then nothing else is an atomic formula. Now they use the word atomic because this came out of logic in the early 20th century. At that time we didn't know. I guess we knew we could break atoms up, but kind of atoms are the building blocks of everything in chemistry, and we don't really think of quarks. Okay, so atomics are the basis of sentences in first order logic. Okay. So they do address the sentence letter thing. The sentence letters of TFL are also formulas of first order logic. Okay, so I misspoke earlier. They are referring to the things from earlier in this. So we're allowing those in our first order logic, although they won't be, happening all the time. Okay. And they're talking now about how they use this script T. You can tell it's a script because it's like a little curly on the left. That's a meta variable, okay? Because we're, again, this distinction between the language itself and the English language talking about that language, you have to keep those separated. And so they're using this as your sort of script characters. And we've seen that in the past many, many times. So, so now we can define what a formula is. Now, a formula are like the sentences of first order logic. So every atomic formula is a formula. So anything we can create this way is considered a formula. So it's natural, right? In English, putting an adjective in front of something that's not negating it, is saying it's of this type. So any atomic formula is a formula. Good. Then it's giving us all the rules about creating formulas using connectives and quantifiers. So if I take any formula and I put a negation in the front, it's still a formula. If I and, or, imply, or biconditional any two formulas, I get a formula. If I quantify universally of something, then I get a formula. And remember, anytime you use a for all, it has to have a variable associated with it. For all, you can't say for all A, right? You have to say for all X, because it's for all something happens. There are logics that allow you to, so one thing that's important in first order logic is that our quantifiers only affect terms and really variables. They never quantify over predicates. Now that doesn't mean you can't do that. I'm just saying you can't do that in first order logic. Second order logic is a logic that allows you to quantify over predicates. So you could say for all predicates, blah, blah, blah. We won't be able to do that within first order logic. Instead, we will reserve statements about all predicates do a thing for the meta language. Okay, it's one of these fine distinctions that logic kind of rips open here. And also we can put it there exists X, some formula. Okay. Now notice this formula doesn't necessarily have an X in it. It doesn't have to. Okay. It can, and it does, but it doesn't have to. And then nothing else is a formula. So that rules out anything else other than things created this way as being formulas. So, you kind of build them up just like you do in predicate or propositional logic. So here's an example of building a formula. So capital F is a predicate, X is a variable, and that is a atomic formula because this is a predicate, and then it's a one-place predicate because there's one sort of place to put a term, and by the definition of atomic formula, F is a one-place predicate and T1 is a term, so then F of T1 is an atomic formula. So this is an atomic formula, and so is this, and so is this. This is a 3-term predicate, and this is a 6-term predicate. So we have 3 atomic formulas here, and they say, well, I'm going to put an implies between these two. Again, that by this rule here, that's a formula. All of these are formulas because they're atomic. This is a formula because they put it implies there. And then this is a formula because you're allowed to put a for all, some variable in the front. And they did say it's a variable. And you have to remember, variables start at S and end in Z. So that's an agreement we're making right now that variables are using only certain letters of the alphabet and names use other letters of the alphabet. We made that earlier, but I just want to point it out again. So then they are anding on another formula, they're putting another existence there, and they're putting another for every there. And we can continue this process sort of indefinitely and get more and more formulas. So you build them up from atomic formulas, and then you get more general formulas. Now, just like before, we have a main logical operator, and it's the thing that was introduced last. Now, by operator, I believe they mean both connectives and quantifiers. So, in this case, the for all X is the main logical operator in this case. So, they say the scope of an operator in a formula is a subformula for which is the main logical operator. So, the scope of for all x is all this junk, okay, and so on. The scope of for all z is all this junk. The scope of there exists y, well, that was introduced after, all this existed, and so it all this becomes in the scope of there exists y, because that's how it was constructed. If you wanted the there exists y to only hit that part, then what you would have done is you would have put the there exists y on this, and then you would have anded the f on. So, you just got to be careful how you're constructing things. Parentheses help. Okay, sentences. So we have formulas, we have atomic formulas, we have terms and so on. What do we mean by sentences? Now, sentences are still the things that are either true or false. So, is this a sentence? Well, I don't think so. Until we kind of have a symbolization of these predicates, it's kind of hard to tell. Because, excuse me, F, G, and S could stand for anything, right? Any predicate. So they're formulas, but until we give them a meaning, whether they're true or not, doesn't matter. So they look at this example. They say, you need a domain for your variables to quantify over. They say, here's my predicate. It's X loves Y, and B is a name. It's Boris. So they say, consider LZZ. Now, LZZ is a formula. That is true. Okay, but like I said, it's kind of not making sense to ask, is it true or false? Because it's a variable. It's not referring to a specific thing. We do at least have, what the predicate means, but again, Z is a variable. It doesn't refer to a specific individual, a specific element of the set of people. But LBB could be true. If Boris loves himself, okay? So that's the distinction they're making here. Again, is a distinction between variables and names, okay? Now, if they took this formula and they put there exists Z in the front, then that's a whole different question, okay? So this formula, it's pretty much unanswerable whether or not it's true or false. This one, though, could be answered, okay? That's a formula that, you could say it's true or false. If there was a person that loved themselves, say maybe Boris, perhaps, then this statement would be true. This one is more difficult to make true, because it would mean that all people love themselves. And probably that's not true, in general. So they want to make a distinction between variables appearing in this fashion, that is with no quantifier attached to them, and variables appearing in this kind of fashion where they're sort of trapped. They're captured by a quantifier. They're in the scope of a quantifier. So that's the difference between a bound and a free variable. If you've had Calculus 3, for example, one thing I do in there often is I talk about what free variables are. And when you're talking about, if you have some kind of equation like, well, let me not do that. But in Calculus 3, for instance, if you have a function of two variables, the x and y are sort of free, but the z, the height, is a function of those. Or, even in Calculus 1, y equals f of x. You think of x in that expression, y equals f of x, as sort of, let me write that down, y equals f of x. You think of the x in here as sort of a free variable. It's allowed to sort of range over any values. But the y is not free. It's depending on something. Okay, it's a dependent variable. That's sort of a loose analogy for what we're talking about here. So, let's be particular, and for logic, a bound variable is a variable that's in the scope of a quantifier. So there's no quantifier in this particular formula, so it is a free variable. Whereas here, that z has that quantifier's scope is this predicate, and so it's bound. Okay, so that's the difference. Bound variables inside of a quantifier, a free variable is not. So they have an example. Let's figure out, I guess, what all the free and bound variables are. So this y is free. Why? because there's no quantifier. There's no exists y. There's no there, for all y appearing. It is free. That x is bound because this quantifier's scope goes this far. Okay, if you think about constructing this sentence from atomic formulas, how would you do it? So you'd start with a few atomic formulas. So ex, dy, lzx. Okay, those are all atomic. You would form ex or dy. Okay, that's a formula. Then you would form for all x, ex or dy. That is how this subformula was constructed, okay, using the construction from earlier. Now, they go ahead and then they say, well, also we could form ex implies lzx, and then we could slap a quantifier there, an exists z quantifier, and okay. Let me put parentheses around these. It makes me feel better. That's how I was taught this stuff. And that's also a formula, okay? Again, we're following the rules. We're taking atomic formulas, we're putting connectives between them to get formulas, and then we're putting quantifiers in the front. So what they're now doing is they're saying this implies is actually the main logical operator, because they're taking, this formula implies this formula. Well, that means that this actually is the main logical operator. It means that this, for all, its scope only goes this far. This exists, its scope only goes, this far. So this x is bound, this y is free. This z is clearly bound, right? It's in the scope of this exists. But the curious thing here is that these x's are free variables. So the placement of a particular variable can determine whether it's free or bound, because this x is bound. It's in the scope of an x, quantifier. This x, it's in the scope of a quantifier, but it's in the scope of a quantifier that has a z in it, and so it's free. So you got to be careful about this stuff. You got to pay attention to where the quantifiers are, and most importantly, what their scope is. Now, if that parenthesis goes all the way to the end here, then all the x's would be bound by that quantifier. But the fact is that all this stuff is bound right inside, this highlighted block. So, the way you construct it matters. If we had constructed it a little differently, and maybe we formed this, then what we did was took this one implies this, and then added the for all. Then the for all's scope would be everything, and then these would end up being bound. So, identifying bound and free variables is, one of these fundamental things you need to be able to do. And what we mean by a sentence, these are things that we can say are true or false, is it's a formula. So a formula meaning something constructed by these rules that we covered, atomic formulas, then combining them with connectives and quantifiers. But a sentence like this is not, a formula like this is not considered a sentence because it has free variables. So a sentence is any formula with no free variables. In other words, any variables that appear are bound by a quantifier. That's the necessary requirement to have a sentence, in the sense that we've talked about the whole semester. That is something that is, true or false. Okay? So bracketing conventions, just use parentheses to make things clear as possible, and you'll be okay. You could go review the old stuff, but my opinion is more parentheses the better. Okay, and that's all there is about constructing sentences. Eventually, we'll use these things in proofs, and so that's it for this chapter.